Each global buffer, that is a BUFG mux, has an associated 2-input multiplexer that drives the output onto a global running resource. These inputs are configured to possibly connect from global clock pins on particular edges of the die or from the BUFIO2 buffers, which are designed to distribute your high-speed I/O clocks. The I/O clocks are designed for low fan-out and maximum performance. This will multiplex 2 clocks together and then drive the result onto a global running resource. The I/O input can be driven directly by one of the 2 global clock pins. The top BUFG can be driven by one on the top edge and one on the right edge. The bottom BUFG, one on the bottom edge or one on the left edge. The I1 input can be driven from a second set of pins on the same 2 edges. Either input can be driven by a BUFIO2 output. So the top BUFG will support 2 BUFIO2s on the top edge and 2 BUFIO2s on the right edge. And the bottom BUFG will support 2 BUFIO2s on the bottom edge and 2 BUFIO2s on the left edge. The BUFIO2 routes add extra delay onto the clock path. The BUFG mux can be driven from a DCM or PLL output as well. And the BUFG mux can be driven directly from the fabric logic if so desired. But the phase of the resulting clock is not controlled. So again, note the BUFIO2 will add extra delay on the clock path when it is used in this fashion. The BUFG mux can also be driven from the DCM or PLL outputs or from the FPGA fabric, but note if you're deriving a clock from the fabric, its phase is not controlled. What all this means is that knowing how the various possible inputs can connect to the BUFG mux may be helpful if you are distributing a large number of clocks. But frankly, I think it is easiest just to build the clocking structures into your design and then let the tools decide how to group clocking resources to the BUFG muxes. For more information on the BUFIO2 cell is given in the I/O clock resources lesson of this module. Likewise, if you're still curious about all the possible connections to the inputs of the BUFG muxes, please refer to the user guide. Every BUFG mux also provides a synchronous switching functionality. This is done by changing the S input, which allows for a glitchless switching of the output. If you're going to use this feature, try to place the clocks to be switched onto the same edge. Again, if you are confused by the discussion of the mapping of the clock pins to the BUFG mux inputs, refer to the user guide for more discussion. If you would like to have an implementation be asynchronous, that can be accomplished by using the clock select type setting of asynchronous. The BUFG mux also supports a standard clock buffer instantiation. This is simply a routing of a global clock. A clock enable functionality which allows a glitchless gating of the clock is also supported. The clock enable functionality saves the user from distributing a global clock enable. In this case, the clock enable input must be synchronous to the non-gated clock. Generally, this will mean that the clock enable be derived by FPGA fabric running on a global clock sharing the same input clock. Now note that all 3 BUFG, BUFG clock enable, and BUFG mux primitives are explained in the Xilinx Unified Library of Primitives, and that is also available at support.xilinx.com like all our other documentation. Now in this slide we want to get into why the DCM and PLLs exist in the FPGA. The answer is simply a clock insertion delay. You see, clock insertion delay moves the sampling window of inputs. The clock insertion delay will increase the clock to output time of outputs, as well as the clock insertion delay is voltage and temperature dependent, and increases require the setup and hold time window. The clock insertion delay can include a global clock input delay, routing to the BUFG from, say, the edge to the center of the die, delay of the BUFG itself, or the delay of a global clock tree to the back to edge. And clock insertion delay is significant, and it should be noted, of course, it's included in the timing analyzer. Now, all of these delays can be compensated with the use of a DCM or a PLL, and fortunately, Spartan-6 has a number of clock management tiles. Now, this is an example of how to remove clock insertion delay in a standard system. In this case, a DCM or PLL is going to be used to deskew the clock, that is, remove that clock insertion delay. First of all, the clock will come in through an iBUFG primitive and connect to a BUFIO2 primitive, which will be the fast way to get that clock to the PLL or DCM. Then that output clock will be routed on a global buffer and at one point it will be fed back through a BUFIO2 feedback. The BUFIO2 to PLL DCM path will be matched to the BUFIO2 feedback to PLL DCM path. This will allow the PLL DCM to keep the in and the feedback in inputs in phase. Therefore, inputs to the BUFIO2 and the BUFIO2 feedback will also be in phase. And this results in no clock insertion delay as measured at the I logic and the IOB. Now please note the BUFIO2 and the BUFIO2 FB should be inserted automatically by the implementation tools. This slide is trying to show you how I/O clocks are handled by Spartan-6. These I/O networks only drive the IOBs on the periphery of the die. Specifically, they drive the iLogic/O logic resources, which are your high-speed SerDes resources. I/O clocks can come from global clock pins via the BUFIO primitive, or they can come from the clock management tile, that is the CMTs, via the BUF PLL primitive. Now there are 4 I/O clock networks driven by the BUFIO2 drivers in every half edge. That is a total of 8 groups of 4, or 32 for the whole device. There are also 2 high-speed I/O clock networks driven by the BUF PLL drivers on every edge, for a total of 4 groups of 2, or 8 for the whole device. In the end, it does not really matter how many possible inputs you have, since the tools will decide the connections to the I/O logic. But the key is to understand the difference between these 2 primitives. BUFIO2's input come from the global clock pins. The BUF PLL's input come from the CMTs. Also, please note there are additional dedicated high-speed I/O clock networks that are used exclusively by the integrated memory controller, which we're really not going to talk about here. And as you may or may not know, Spartan-6 contains a dedicated programmable memory controller on the device. The BUFIO2 is designed specifically for the use with the iSerDes and OSerDes resources. In addition to driving the I/O clock output onto the I/O clock network, this buffer can also generate a divided clock and chip enable required to manage the data transfer within the iSerDes resources. These are located in the center of each of the 4 edges. The input I will come from the global clock pins or the GTP clock output pins on the same edge, and that would of course be coming from the MGTs or serial gigabit transceivers. The I/O clock output will drive the I/O clock network for clocking the I/O logic and the high-speed clocks of the iSerDes. The divided clock or div clock output drives BUFG or CMTs in the center column. The frequency is divided by using the divide attribute that is associated with the BUFIO2 primitive. It's intended to drive the clock div input of the iSerDes, among other things. We'll see this a little later on. Likewise, it also generates the SerDes strobe output, which drives the I/O clock enable of the iSerDes resources. This is asserted for 1 I/O clock period out of every divide to transfer data from the I/O clock domain to the div clock domain, or vice versa, depending upon the use of the SerDes. Timing of the SerDes strobe ensures maximum time for clock crossing. So again, note the GTP clock output pins are the output clocks of the GTP transceivers. We're really not going to get into the transceiver functionality here in this module. And the SerDes strobe, which is intended to be connected directly to the I/O clock enable input of the SerDes, determines which rising edge of the I/O clock should be used to launch capture data going to or from the div clock domain. The div clock output of the BUFIO2 has a dedicated connection to the center column of the chip where it can access the BUFG and the clock management tile resources.